All right, everyone, welcome to our webinar. This is the crystal orientation using the Laue method, brought to you by Precision X-ray and Photonic Science with our featured guest, Gavin Hester from Brock University. A few ground rules before we get started. Everyone is muted and no video other than the panelists. Down at the bottom of your screen, there should be a chat function for Q&A. So you can either use the chat box for the Q&A or you can actually use the Q&A box. So we will go through the presentation first, and then we'll open it up for the Q&A after everyone has given their presentations. Any questions, please feel free to let me know. We will be recording this, so it'll be available after the webinar for those people who registered and weren't able to attend, or if you needed to get some additional information. And with that, I'm going to introduce Rob Brooks. So we can just, there we go. Rob is our senior test engineer from Photonic Science. He is responsible for production testing of scientific cameras and X-ray systems. He joined PSEL in 2009, and his intimate experience with Laue system design, setup, testing, installation, and commissioning at customer sites, as well as remote support. So from that, Rob, I'll have you take over. Don't forget to unmute.
Hi, Debbie. Hi, everyone. Thanks for listening in. So I'm just getting on to the next slide. Here we go. So yeah, I'm going to say a few things about Laue diffraction generally, and then I'm going to talk about the systems that we make here at Photonic Science. So Laue diffraction is named after this gentleman here up on the top right-hand corner, Max von Laue. He was a German physicist. And he proposed and predicted and did an experiment to show that if you shine a collimated X-ray beam towards a crystal, then the beam will diffract from the planes of atoms in the crystal. He used collimators in between the X-ray source and the crystal to ensure the beam was essentially parallel when it hits the crystal. And you need to use a polychromatic light source that is like a X-ray source, that has a range of wavelengths because the diffraction that is produced is uses the full range of wavelengths that come from the source. So he showed that if you did this, you could observe spots on a photographic plate from the diffraction, and these spots are essentially a superposition of diffraction from sets of planes in the crystal. The distribution and symmetry of these spots relates to the structure and the orientation of the crystal. So he did this experiment in 1912, and he was given the Nobel Prize in 1914. So this technique's been used for maybe 90 to 100 years or so in this form, using photographic plates to study crystals. And it's perhaps not as popular as other techniques. It's quite complicated to analyze the results, and it takes time and patience to acquire the images and analyze the patterns, which used to be done by measuring the spots in the image and referring to charts, etc. So in the bottom right hand corner here, you can see a diagram, so that you can see the X-ray beam coming in here and hitting a crystal, and the X-rays diffract from the crystal and hit this plate here, and that's called transmission Laue. And on the right, this is the backscattered method, which is the one we use on our systems, where the X-ray beam passes through the detector, hits the crystal, and then the X-rays are diffracted back onto the detector plane. So, as I say, this has been around. This method's been used for quite a long time, but more recent improvements this century have moved things on quite a bit. The development of the digital camera, CCD-based X-ray cameras, allows improved sensitivity and ease of use. You don't need to use photographic film anymore. So Photonic Science developed a camera in about 2004, and that was used in a lot of labs where people would exchange their film-based cassette imaging device with a CCD camera. Also, the development of Laue indexing software aids Laue pattern analysis, so you don't have to refer to charts anymore. You can put in the lattice constants and space group, etc., from your crystal, and you can simulate the crystal in different orientations on a computer, and you can use this to match your pattern that you've acquired experimentally. Improvements to the performance of computers, higher CPU power, enables fast indexing of the Laue patterns using this software. So within a few seconds, you can fit a pattern that you've acquired and work out what orientation your crystal is in. Polycapillary X-ray focusing optics allow efficient use of available X-ray flux. This enables you to use low power X-ray sources, but get a high flux on of a high power density of X-rays onto your crystal. This minimizes exposure times you need to do on the camera, so you can actually get real-time video rate images back from the of the diffraction patterns back to the detector. Development of mini and micro focus sources and also narrower cone angles also reduces the spot size, the X-ray spot size on the sample, and also increases your X-ray flux. So different crystals have different patterns, and crystals are grown and used in a variety of fields and applications. I've listed some of them here, and the properties of crystals can vary considerably depending on the orientation. So you might need to measure the orientation, and so a Laue system can do that for you. You can also use them for measuring a range of things here: crystalline phase and structure, thin film analysis, texture evaluation. Are used in for semiconductor crystals, superconductors, analyzing geological materials, investigating sample stress and strain. People growing crystals often also want to cut them, normally cut them across a particular face, such as 100 or something like that. And a Laue system will enable you to align the crystal so that you can then remove it and put it onto a cutting tool and cut across the face. They can be used in industry for process quality control. For example, if you're growing synthetic diamonds and you want to use it as a quality control measure, you can put a tray of these into the system, and it will scan between them and obtain diffraction patterns and analyze the diffraction patterns, and you can see how well aligned your crystals are. They can be used for checking the quality and orientation of nickel alloys, nickel alloys for gas turbine blade manufacturers also. Laser crystals, piezoelectric crystals, for example, used in fuel injectors, and the alignment of these is important as well. It's also used by solar cell research. I've actually got another slide further on about silicon wafers that relates to that. Here's an image of our new Laue system. We use an X-ray source with a narrow beam focus, which allows you to have extremely small sample sizes, as well as large samples. we have a CCD camera, which acquires the backscattered X-rays. This has got high resolution and high sensitivity. We have stages, motorized stages that allow you to drive the sample around and position it under the camera. And you can also have, like I was saying, have a tray to scan a range of samples, or a goniometer, which you can use to align the crystal to a particular face once you've indexed it. We have a distance measuring tool inside as well, which allows you to measure the distance between the scintillator and the crystal, and that's important for when you're simulating the crystal structure, when you're simulating the diffraction pattern to allow you to index it. The system comes with the software that you need to acquire the images and the pattern simulator, and it allows you to do misorientation measurements to a particular face with 0.1 degree precision. Next slide. So this is an image here showing our system. So at the top, you've got the X-ray source here. This shines an X-ray beam through the Laue camera with this rectangular box here. We have a visible camera mounted at the front, and this enables you to view the sample, looking down at the sample to choose the area of interest on your sample. And you can then drive it back under the laser tool to measure the distance and get the distance set correctly, so that you're at the focal point of where the X-rays come down here, and get the correct distance. The crystal mounts onto here. You have a little point if it's a small crystal to put it on, or you can have a flat surface which you can attach it to. These can then be removed and then attached to a goniometer on a wire saw or something. So once you've actually done the alignment, you can transfer it to the tool that you want for doing the cutting, if that's what you want to do. This part here is the goniometer, and this is a 2-axis tilt stage and a rotation stage underneath that allows you to rotate the sample around the beam. And then below this, you have a 3-axis positioning set up here, which allows you to move in X, Y, and Z. Next slide. So this is a close-up of the arrangement at the top of the camera. So this is the X-ray source here. The camera's here, this black box, and you have your laser distance tool here, and this is your machine vision camera here with a telecentric lens. And this has got a coaxial illuminator on it as well to light up your sample, so you get a nice sharp image from it. So here's an example of a silicon pattern. So you can see there are white spots, which are the diffraction spots in the image, and these are overlaid with green spots, which are the simulated spots. So you can see this pattern has been indexed, and it gives down here, it gives the information on the angles, and then here it's been aligned on the with the goniometer to give you an aligned pattern. This is another example here. This is a mineral sample. This is an aragonite sample, and these were very small samples, less than a millimeter, that we were able to index. Here you can see the index pattern. So on the left you have the image that the detector sees, and then overlaid here you have the simulated pattern. You can also use it to see defects in your crystal. So this example here on the left, this is a cubic crystal, and you can see that some of the spots have become stretched, and that's an indication that there is stress in the material. And this one on the right here, some of the spots have become double spots, and this is caused by twinning, where you have two orientations the crystal within the same grain of the material. We've also made some, well, we've made a range of these systems with different features. This is one of the more complicated ones we did. Was it had a wafer scanning system built into it, so you could place a large polycrystalline wafer on the surface, and you could map it with a visible camera with off-axis light illumination, and that reveals the grains in the material. And this is silicon, and then you can centroid the positions of these grains, and you can automatically drive the stages around so that it positions the wafer, the different grains in the wafer, under the Laue camera. And then the Laue camera will acquire the images, and the orientation is then measured automatically. And then you get a map, a color map, a false color map here, and the colors refer to the different orientations of grains in the image. You can refer to this Euler triangle on the left that shows the what the colors mean. Visible camera allows detection of grain boundaries. And yes, okay, I've already explained that bit. Okay, so that's it. Thank you very much for listening.
Okay, I do have one question from Mohammed, and Mohammed, I'm going to give you permission to chat. So go ahead and ask your question.
Hi, Mohammed.
Is he there?
I think he's muted.
You got to unmute there, Mohammed. No, maybe not. Has to unmute. Okay. Well, we'll have him hold off then. All right. Well, thank you very much, Rob. That's a little background that we had on the Laue system. And now we're going to get into some of the fun part of it. Dr. Gavin Hester, our assistant professor from Brock University, is going to speak on his experiences using the Laue system. So Gavin is a part of a group at Brock University in Ontario, Canada, studying crystal growth and characterization of new quantum materials. Currently, his main focus is a ceramic material called terbium silicate. And Gavin's years of use with the Laue system was a central part of his thesis. So with that, Rob, I'll have you stop sharing and Gavin can begin to share.
All right, great. You should be able to see my slides now, Debbie.
Yep, thank you.
Great, yeah. Thank you all so much for coming to this webinar. And thank you to Precision and Photonic Sciences for setting this up and giving me the opportunity to talk. So today I'm going to be talking about, as you might imagine, some Laue X-ray diffraction. And I'm particularly going to be kind of giving my kind of very niche area of physics use for it, which is in doing crystal growth and preparing for neutron scattering experiments. So a little bit of an outline. So my very specific focus is in new quantum materials and specifically quantum magnetism. So first I'll give a little bit of an introduction to that for those that may not be familiar. And then I'm going to discuss this, this compound ytterbium silicate, where we discovered this new quantum state that was not expected for a system based off ytterbium atoms, as this one is. And in there, I'll talk about our crystal growth, how we use the Laue for that. I'll briefly talk about some heat capacity and ultrasound velocity measurements, which also required a Laue. And then I will kind of divert a little bit into giving you a very broad view of what neutron scattering is, because it's not something that is that well known to people outside of the neutron scattering community. I'll discuss why we would use neutron scattering, and then finally I'll show you some results we got on ytterbium silicate, and tell you a bit of an interesting story that does involve the Photonic Sciences Laue that I was using. So with that, let's jump into quantum magnetism. So first I'll talk about magnetism in materials, because maybe not everybody in here is a material physicist. So there are kind of non-magnetic and magnetic materials. So if I handed you sodium chloride, and you wanted to know if it was magnetic, you would kind of sit down and you'd write out where the electrons are in each of their shells, and you would see, okay, as we expect, sodium chloride has filled electron shells. So there are no unpaired electrons in sodium chloride, and so it's not magnetic. And if you don't believe me, you can put a magnet up to your table salt. But then there's iron oxide, which is actually the first magnetic material humans ever discovered. And if you do the same routine of figuring out where the electrons are, you'll see that there are 5 unpaired electrons in iron. And since electrons have an inherent magnetic moment, if they're not paired to compensate one another, you get a magnetic material. Now, this magnetism can arise in a few different ways, and kind of the 3 classical ones. The first one would be the ferromagnet. So this is what holds your children's pictures to the fridge and things like that. And is certainly a fundamental piece of modern technology. So all the spins here are parallel to one another. Nothing too exciting there. And we had discovered ferromagnets, in ancient times. We didn't really understand why they were magnetic, but we knew they existed. And then there's the antiferromagnet, where you have each spin is compensated by another spin that is pointing in the opposite direction. So you have no net magnetic moment to your system. So if you put a magnet up to it, it would do nothing. But you still have magnetic moments. And it took us until about the 1950s with neutron scattering to actually prove that these types of systems exist. And then just as kind of a completeness, if you heat up a ferromagnet or an antiferromagnet, eventually the temperature becomes so high that the bonds holding the spins parallel or anti-parallel become too weak. And then you just get this random orientation of spins. So that's some language to kind of get us the basics of magnetism. And then we go into quantum magnetism. So the classic example in quantum magnetism is putting antiferromagnetic spins on a triangle. So if we start with the top spin and say it's pointing down, we can go to the second spin and we know that that has to be opposite. But then you can kind of immediately see that this third spin doesn't know which direction to choose. It is energetically unfavorable for it to be up and down. And what happens is if you tile this over a lattice, making kind of a triangular lattice like this, you get what we call macroscopic ground state degeneracy, which is a lot of buzzwords, but it's essentially saying that there is no single energy state for the system to enter that is preferred. Generally, systems always look for the lowest energy state, but since you have this kind of uncertainty in what that spin's direction should be, it means that you have this very large degeneracy to the ground state. And what we hope that leads to, and this is kind of our holy grail in quantum magnetism, is the quantum spin liquid. And so this is thought to occur when you have this ground state degeneracy. When you cool the system down, eventually quantum fluctuations take over, and every spin within the system becomes entangled with every spin, with every other spin in the system, making 10 to the 23rd atoms all entangled together. And this is really ultimately what we're looking for, but it turns out it's a very hard thing to find. And so it's often you kind of shoot the arrow and you draw the target around where the arrow landed. But that's really what we're going towards is these very new exciting quantum states. And then if you're not in this field, you might wonder, why do we bother studying these systems? Most of their transitions happen at helium temperatures 4 Kelvin or less. And there are actually a number of reasons. So one is superconductivity. So this quantum spin liquid state was actually introduced in, if I remember correctly, the 1980s by Paul Anderson as an explanation for why type 2 superconductors are superconducting. It turns out he was wrong, but it has turned into a whole field of its own in looking for interesting quantum magnetic states. And then, the kind of current hotness, aside from AI right now, is quantum computing. And so the idea with quantum magnetic systems is that you often get what are called topologically protected states. And really all that means is that if some external noise comes into the system, it will not break your quantum system. Whereas if it was something like an ultra cold gas, it would. And governments want quantum computers because they can break standard encryption algorithms. And so they can, read encrypted emails and things like that. But then maybe on the nicer side is the idea of quantum cryptography, where you similarly use the ideas of quantum mechanics to instead prove that no one is stealing your data. And so I really like this quote from Richard Feynman that says, nature isn't classical. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And so this kind of hints on another use of quantum computers, and that is better understanding quantum systems like the one I'll be talking about today. Okay, so with that, I want to jump over to talking a little bit about ytterbium silicate. And so we're talking about Laues, so obviously I have to talk a little bit about the crystal structure. And so here on the left is the crystal structure of ytterbium silicate. It's a monoclinic system, and oh, Muhammad, okay, perfect. The teal or green atoms are all the ytterbium atoms. Those are the ones we'll focus on because they are what hold the magnetic moment in the system. And you'll see that this system is kind of squished, I would like to say. So you don't have a perfect honeycomb. You instead have a honeycomb that's kind of elongated. And that actually gives rise to many of the properties I'll be talking about today. But there's always a slight aside I like to make here because it's something that I think is just one of the most cool scientific things. So what I'll be talking about today in ytterbium silicate all occurs at temperatures below about 200 millikelvin. So here you get quantum entanglement, this idea of Bose-Einstein condensation and magnetism. But as we were working on this project in my PhD, we actually found this system was already very famous. Because if you go to temperatures in excess of, say, 1500 Kelvin, engineers at places like NASA and stuff actually use this compound to coat jet engines to protect them from being degraded by hot gases and water vapors and things like that. And so we've actually done some kind of cross-pollination projects with some of those groups, supplying them samples to try and better understand the high temperature properties. So not that relevant to this talk, but I think it's just a very good instance of keeping in mind that maybe a material is not interesting to you for a certain reason, but in a whole nother regime, it could be interesting. And so I'll talk a little bit more about the crystal growth because we used the Laue pretty extensively in this. And the method that we used was called the optical floating zone method. And in this method, you basically take a feed rod at the top. So let me get my laser pointer here. Feed rod here. And so this would be a compacted rod of polycrystalline material. So if you were making ytterbium silicate, you would do the reaction, get it to be pure ytterbium silicate, and then kind of harden it into this feed rod. And then at the bottom, you mount what is called a seed rod, which is normally some powder, compacted powder, maybe with a previously grown crystal on top. And then what you do is you counter rotate these two rods and you place them within a set of elliptical mirrors, which are these yellow things here on the side. And these are, 1.5 kilowatt bulbs each roughly, depending upon what growth you're doing. And they focus using mirrors, all of that light right onto the interface between those two rods. And then you slowly move those mirrors up. And as that system cools down, when it leaves the intensity of the light, you form ideally a single crystal that you can then use for your experiments. And so this is what the system actually looks like. It's a little bit hard to tell because they are elliptical mirrors, so they don't photograph very well. But if I overlay this diagram on here, you can hopefully get a little bit better idea. And so actually, rather than moving the rods here, actually this whole stage of metal moves up as you're doing the growth. And so when we did the growths, these were actually started by a couple of former colleagues of mine during my PhD and then kind of continued on by me. So this is what our crystal as grown from the floating zone furnace was. So down here at the right side where it's dark, that's where our seed crystal was. And then we kind of grew off of that. And if you're familiar with crystal growth or particularly optical floating zone furnaces, you'll notice that this doesn't quite look right. And if this were one big single crystal, then it should be kind of nicely faceted, all one color, not cloudy. But it turns out that actually that is not how this system likes to grow. We end up having to basically take a hammer to these crystals to break them into little pieces. And so we get pieces like this, which are on the order of 5 or so millimeters on each side. And this is kind of where we had to have a Laue, because due to the way this grows, it doesn't grow along nicely faceted faces. So there's no way you could align this crystal by eye at all. So you have to put it in a Laue and then you have to do the cutting, kind of like Rob was talking about. And so that's actually what we ended up doing for our neutron scattering experiment. And so here at the top, this is a copper mount that mounts to a refrigerator in a neutron scattering instrument. And then we have these long spindly copper legs that go up to these little plates of copper that we have strapped down and glued crystals to. And so what we're doing here is, since ytterbium silicate doesn't grow as one large crystal, we need more mass to actually get a measurable signal with neutron scattering. And so we basically use multiple crystals all aligned in the same direction to act as one larger crystal. And so here there is roughly a gram of crystal that got co-aligned in this experiment. And so we then, strap these down with some copper thread, and we actually use a fluorinated glue to secure them to the system. And that worked out quite well. And if you're interested in more of the details on the synthesis of this, we do have a synthesis paper that came out. And so there's the reference there if you're interested. Okay, so that was the crystal growth. Now let's discuss the physics of the system a little bit more, since I'm a physicist. That's what I like to talk about. So the state that this system exhibits is the quantum dimer magnet state. And I kind of think of this as the textbook quantum state. If I was writing a textbook on quantum magnetism, this is the thing I would introduce people to. And so I'm going to introduce some equations here. So please forgive me being a physicist, but I promise I'll try to explain them as good as I can. And so in the case of having a system with two electrons, say, if these electrons entangle with one another, they enter the same kind of singular wave function, then the ground state of that system would be the two electrons pointing in opposite directions. But since they're quantum particles, you can't say one is up and the other's down. They have to be in both states at once. And then in an early quantum mechanics class you would take as an undergraduate physics major, you calculate the excited states of this system. And so you get a state with both the spins parallel to a arbitrary z-axis. One state where they're again coupled opposite one another but in superposition. And then finally a state where they're anti-parallel to the field. And so what's important about this is that all of these SZ numbers are actually called quantum numbers. And there's an important property in quantum mechanics where if you have an integer quantum number, so 1, 2, 3, 4, 0, etc., then the system must follow what's called bosonic statistic. And really what this means is that Pauli's exclusion principle doesn't apply. And Pauli's exclusion principle says that two electrons can never be in the same exact quantum state at the same time. But it turns out if you entangle the electrons, then they can all enter the same quantum state. And so this kind of allows us to go to these more exotic systems where you can be all in the same state. And so what this might look like on a lattice, I've already shown you ytterbium silicate, so you probably recognize the lattice here, is if you have these two nearest neighbor spins that entangle with one another. And so this kind of squished honeycomb motif of this system naturally leads it to enter this dimerized state. And so this is all there is to the ground state. And this, I would say, is interesting, but is maybe not too revolutionary to people that are in the field of quantum magnetism. But then there's the idea of what happens when you apply a magnetic field to the system. So here I'm showing the same wave functions, we would call them, as before. And now I'm showing you kind of what happens to each of these three excited states as we apply a magnetic field to the system. So since the SZ equals 1 state is parallel to the field, as you increase the field, it's only going to be more and more energetically favorable for it to enter that state. And so it turns out when the bottom of that SZ equals 1 state reaches 0 energy, so the ground state, as we would say, the system can be described as a Bose-Einstein condensate. And it's actually a Bose-Einstein condensate in that the ground state is made up of this S equals 0 state, this top one here, and this other excited state. And so you get two critical fields. So if you're measuring your properties as a function of field, you should see a transition at 2 temperatures that corresponds to this idea of Bose-Einstein condensation, which is a state where, because they're bosons, they can all be in the same quantum state. And so when you cool the system down, a Bose-Einstein condensate, all of your particles enter the exact same ground state. And so this is something we've seen in various types of systems. We've seen it, we think it exists in neutron stars. We've seen it in ultra-cold gases. It exists in type 1 superconductors, exists in helium-4. many, many different places. This is a very universal type of physics that we've seen and has even been lauded as the fourth or fifth state of matter in our universe. So understanding more about these systems is only going to help us understand the general idea of Bose-Einstein condensation more. And so I think the best way to actually explain this is maybe rather than equations, showing you a video or an animation that I made showing what happens. So at first, we're going to be in this quantum dimer magnet or quantum paramagnet state. It goes by many names. And the spins are going to be randomly fluctuating, quantum fluctuating, we would say, around. And then when we hit this first critical field, you'll see the spin suddenly lock into place around the field direction, which in this case would be coming through the plane of the honeycombs. And then finally, we'll see at the second critical field, all the spins are parallel. So yes, here spins randomly fluctuate. They have no net direction. But then suddenly at one field, they all break their symmetry around that field and lock into place. And so those of you more versed in magnetism might say that's just an XY antiferromagnet, which at some level it really is, but it's important that it maps to this Bose-Einstein condensate because it's what allows us to actually understand the physics. So here I'll let it go again. The spins suddenly lock into place. They, in theory, could have chosen any direction around the field, but for them to be a Bose-Einstein condensate, there must be only one direction they choose around the field. And so now I'll quickly go over our bulk measurements because I don't want to go too far into detail on these. But generally what you do with these systems is you first want to figure out their phase diagram. What happens when I increase the temperature, increase the field, etc. And so here I have our phase diagram for ytterbium silicate. So this would be for a field going kind of perpendicular to the honeycombs. And so at low field, we're in this quantum paramagnetic state. So your spins are not locked into place. So you would see no net magnetic moment. You wouldn't see magnetic Bragg peaks if you were doing neutron scattering. It just kind of looks like a paramagnet to the outside observer. But then once you reach, in the case of ytterbium silicate, about 0.4 Tesla, which is a critical field smaller than any other Bose-Einstein condensate measured in solid state systems like this, you suddenly break that symmetry, lock those spins into place. And so we classify this as an antiferromagnet. But again, this could also be called a BEC or Bose-Einstein condensate. There is kind of this vertical line here that indicates this mystery regime. So this would not be shown in my animation. And this is something I'll talk about a little bit, but I'm happy to answer more questions about because we see some definitive change in the heat capacity and ultrasound velocity kind of between this field of about 1.2 Tesla. And then eventually you reach the second critical field at 1.4 Tesla. Now all your spins are parallel to the field, so treating it as a Bose-Einstein condensate no longer becomes useful. And so with that, I'll kind of quickly jump into neutron scattering. And so I'm a big fan of history, so I always like to give a little bit of history because I think it shows us how far we've come in the sciences and what we can learn from the past. So in order to do neutron scattering, first we had to know the neutron exists. So it was actually discovered by this gentleman, James Chadwick, in 1932. And I think it's very interesting because the paper he published on the discovery of a brand new particle that makes up virtually everything we see was less than a page long, had no figures, and basically just he argued that he bombarded beryllium with alpha particles and he measured the recoil of some nitrogen and basically was able to deduce that there must be something with the same mass as a proton but no charge. And so it baffles me that there is a one-page paper on the discovery of a brand new particle, especially if you see these big particle physics papers nowadays. But after that, kind of then, the World War II happened. And so people had started thinking of using these neutrons for things. So in 1936, a group tried to do a neutron scattering experiment. This isn't their data, but their flux was so low. The number of neutrons coming into their system was on the order of counting 10 neutrons per minute. And so you can imagine that will take a very, very, very long time to measure. And so it was not really followed up on until after World War II was done and followed up at Oak Ridge National Lab by these two gentlemen, if it will show up, there we go, Clifford Scholl and Ernest Wolin. And actually, I believe Scholl won a Nobel Prize for the work he was doing here. And what they did was they put gypsum and rock salt, shown here on the left, inside of a beam of neutrons that they had all chosen a single wavelength for. And then they have a helium detector back here that they count the neutrons at. And so they can see these Bragg peaks from the system by using neutrons. And this was really the first modernly recognizable neutron scattering experiment. And so this was in the 1950s. And so we've been developing this technique as a physics and a really general science community for the past 70 years. And we found many, many different ways to use neutron scattering. So this is kind of a diagram on the left showing all the different techniques of neutron scattering. I won't go into all of them because some of them are very niche that I don't even use. But importantly here on the x-axis, we have reciprocal space Q, or you can think of it as just the length scale of what you want to measure. And then the y-axis is the time scale. So if you're measuring some change or motion, how quickly of a process can you measure? And really what I want to point out here is you look, and neutrons can cover things from, say, almost 1,000 angstroms to less than an angstrom. And it can measure time scales from 10 to the minus 7 seconds, so 10 microseconds, to 10 to the minus 14 seconds. And so it just has this huge range of applicability. And actually, I think it was Bertram Brockhaus who also won a Nobel Prize for neutron scattering that said, if the neutron hadn't existed, we would have needed to invent it. Because it just so happens that the neutron's mass gives it an energy and a wavelength that lets it kind of be able to scan these large ranges of length scales and time scales. And we can use that to our advantage as material scientists. And so kind of four of the kind of often lauded parts of neutron scattering that are advantageous is one that it's non-destructive. So you get your sample back out. You are obviously irradiating it, so it may take a year or so to cool down, depending on what it's made of. But more importantly, the neutrons are highly penetrating, so they don't have a net charge. So if, say, your sample needs to be inside of a cryostat or a magnet or any variety of things, the neutrons will generally just go right through that and not care. And you can deal with it as a background later on. And that's really, I think, one of the things that has made neutron scattering so prevalent, especially in comparison to X-ray scattering, because you don't have to do a lot of extra work to have a sample environment and things like that. Additionally, important for my research is that the neutrons have a magnetic moment. So they have no charge, but since they're made up of these quarks inside that have, I believe one of them has 2/3 charge and the other has 1/3 charge, you you can think of a coil of wire inside of the neutron to give it a magnetic moment. And we can use that to probe the magnetic properties of a material. It's sensitive to light elements, which is something you really cannot say for X-ray scattering. Particularly hydrogen absolutely loves to absorb neutrons. And this is actually both a blessing and a curse. So I mentioned using fluorinated glue earlier. This is why we have to use fluorinated glue. If we used normal glue, it has so much hydrogen in it that you will never measure anything in the history of the universe with neutron scattering. And then finally, I've already kind of alluded to this, but the energy of the neutron is ideal for seeing the types of atomic motions that solid state physicists care about, and now even biophysicists and many other fields. So that's kind of the basics of neutron scattering. I want to go a little bit into how neutron scattering experiments work, and I'll kind of connect this at the end to our neutron scattering measurements and Laue diffraction a little bit. So there are two ways that neutrons are generated. One is via a nuclear reactor. So you get a rod of uranium-235, you start bombarding it with neutrons, it becomes radioactive, and ideally releases more neutrons than you put in to start the reaction. And so this on the right is actually a diagram of the high flux isotope reactor at Oak Ridge National Lab in the US. And so I'm not going to go into detail on this, but I think it's kind of comical to think about what we really do as neutron scatterers is ask the nice nuclear engineers if they will just kind of drill a hole in the side of their nuclear reactor for us and put in a beam tube to just allow some of those neutrons to leave the reactor rather than cause another fission event. So it turns out the high flux isotope reactor actually has a number of these beam tubes because it was designed for this, but this was kind of the initial idea of how to make neutrons. The more modern way to generate neutrons, although both are still used for sure, is to use spallation. So spallation is a bit of a complicated process, but essentially what they do at Oak Ridge National Lab, which I'm showing in this diagram here on the right, is that you build a particle accelerator. And so that's what this red line is here. And so they accelerate protons to some near fraction the speed of light. They actually accumulate them first to get a large amount of them. And then they send them down this tube and slam them into a mercury target. And those protons are such high energy that when they hit the mercury, you can think they kind of make it explode. And that releases more neutrons that then they guide to all of these instruments in these lines kind of showing off here. And so these are kind of the two ways to generate neutrons. They have benefits and advantages to each. But really the point here is that it takes massive government facilities to build these systems. Either you need a nuclear reactor, which is heavily regulated, or you need a ton of space and money to build a spallation source like this. And so once you've got your neutrons and you've got them to an instrument, let's talk a little bit about the neutron instrumentation. So on the left is a time of flight spectrometer. This is actually the cold neutron chopper spectrometer at Oak Ridge National Lab. I won't go over all the things labeled here because they're not super important, but what happens is the neutrons come in here from the bottom left down this yellow tube. We send them through these choppers that basically select for a single velocity of neutrons. And then eventually they go and they hit the sample, which would be in this little red area here. And just for a sense of scale, there is a person for scale here. So this is, 2 or 3 times taller than your average person. Absolutely huge instruments costing millions of dollars. And so once the neutrons get to your sample, they then bounce off your sample. And in reality, almost all of them will not interact with your sample at all. But if you have enough, it will occur often enough that they will bounce off your sample at some angle and hit one of these green detector rods, which are filled with helium-3. And you then detect the neutron. We know the neutron's energy by measuring the time it takes for this process to happen. And so we can then get momentum and energy resolution for the neutron to then back out the physics happening within the system we scattered off of. On the right is kind of an instrument that can do a similar type of experiment, but this one is geared towards being in a reactor. And so here, this is a triple axis spectrometer, kind of one of the first neutron instruments developed. And here you send a beam of polychromatic neutrons, basically just coming out of the reactor, through what's called a monochromator, which is just a crystal, often silicon or germanium or something that is very nicely crystalline. And based off the angle of the bounce off the monochromator, that selects for a certain energy. And then again, you guide it to a sample space here. And then you again, here you only have a single detector. So you have a detector arm that moves around and you can analyze the final energy with basically another monochromator crystal and then detect the neutrons with helium-3. So that's a very quick overview of how neutron instrumentation works. I could give a 2-hour-long talk on this if necessary, but moving on from that, I want to talk a little bit about the logistics of this because it's often something that gets overlooked. So neutron scattering, like I said, is done via these government sources. And so the one that I've often used is at Oak Ridge National Lab, but there are facilities around the world. And so due to the nature of how these facilities work, you generally start with a semi-annual proposal call. So you have 2 times a year that you can propose neutron experiments. And so you submit your proposal, and over the course of about a couple months, it undergoes peer review as well as feasibility review. And then after that, you are either awarded beam time, you are rejected, or you are given alternate status, which I like to think of as a maybe status. And so this is all, this requires planning, on the next year's time scale for your experiments because you only have these proposal calls so often. And just to kind of give you some numbers to put to this beam time process. So this is the plot here on the left is from 2021 to 2023 for the spallation neutron source at Oak Ridge. And I've highlighted particularly the instrument that I used for the measurements I'll show, which is CNCS. And so you'll see the blue line is the total number of people that wanted beam time, and the orange line is the total number of people that got beam time. So in the case of this instrument, you're looking at roughly a 1 in 4 chance of getting beam time if it were purely on chance. And you'll see some instruments are better, some are worse. CNCS tends to be one of the most oversubscribed. But even just for the last call, you can see on the right there, we had almost 900 proposals submitted. Only 175 were awarded time, so 20%. 162 were considered alternate, so maybes, and the 519 of them were rejected. So this is a very, very competitive field to some extent, especially right now for a myriad of reasons that I won't go into. But I think this particular issue will get better. But what I'm trying to drive home here is the value of this neutron scattering time. So if you just look at it on a numbers basis, let's see if I can hide this. There we go. On a numbers basis, you have the facility construction. So for the case of Spallation neutron source, that was $1.4 billion from the federal government. And that was in 2006 dollars. So I think it's closer to 1.8 billion now. And then you have the single experiment overhead, which in 2014, Oak Ridge said that it cost them almost 300,000 US dollars per experiment to run. That includes materials and supplies, electricity, plumbing, water, the instrument scientists, and all of the myriads of support staff that you have to have for these types of experiments. Now, luckily, since I'm an academic, I don't have to pay for that. But there are people in industry that use neutron scattering. I know particularly automotive manufacturers use it for studying stress and strain in their parts. And so they end up paying about $10,000 per day to use the neutron experiments. But then there are definitely costs to the individual researchers like myself. So for me to travel to an experiment, if I'm sending multiple students, you're looking at about $5,000 an experiment. And then sample synthesis, depending on what you're making, can easily be $1,000 to $10,000 per experiment. And that's just on a materials basis, not even factoring in time and instrumentation that you would assume you already have. So $15,000, you know, is a rough guess for how much it costs a neutron scatterer to do their experiment. And so with that, I want to go over to now talk about the data, and then we'll come back to a little bit talking more broadly about neutron scattering. So yes, I did some inelastic neutron scattering experiments. This was actually right when I started my PhD. So I think I was in classes during the experiment. So some of the individuals from our group went and did the experiment, and then I was given the analysis to do afterwards. And so here I'll be showing you on the left, it'll be the phase diagram that I've already shown you. And on the right, it's going to be our neutron scattering data. So in the top right, if you're very familiar with neutron scattering, this is the direction we take in reciprocal space to make this plot. If you're not, you can purely ignore that. The x-axis here, I've labeled it with reciprocal lattice points, but for all intents and purposes, just think of it as the momentum transfer of the neutron. And then the y-axis is the energy, so how much energy the neutron lost to my sample when it hit the sample. And then the color scale is the intensity, with blue being very few or no neutrons, and yellow being a lot of neutrons counted at that point. And so the first thing I want to point out is actually not even shown here, but we don't see any Bragg peak at 0 Tesla other than those from the nuclear structure. So this indicates that there is no magnetic ordering, which is consistent with that idea of the quantum dimer magnet that I showed before. But really the smoking gun that we have that system is that we have this yellow wave through our data that is actually a triplon excitation. So if you remember that single ground state equation I gave with the 3 excited states, this is basically measuring the excitation from the ground state to one of those excited states. And so condensed matter physicists, we love our quasi-particles. And so we call this a triplon. You could also kind of think of it as a spin wave or a magnon, but there are some nuances to that. So here we've confirmed we have that quantum dimer magnet state. When we apply the field, eventually we enter this BEC or anti-ferromagnetic regime. And this is where things start to get really interesting. So probably the most prominent change, so we still have this spin wave excitation here, which now you could call it a spin wave more accurately. But the most important thing we see is the development of this mode down here near 0 energy. And that's what's called a Goldstone mode. And now if you remember in my animation, when those spins locked into place, you can imagine that if I push one spin, it can spin every other spin in the system. And so this actually ends up being kind of a new mode to excite the system. I can now use a neutron to start spinning the moments around the magnetic field. And so that's what we're measuring there. And this is indicative of that circular symmetry breaking that is required for a system to be Bose-Einstein condensate. And so this is our best smoking gun that we have a Bose-Einstein condensate. But then we do have some kind of other artifacts in our data, like this kind of fuzz that exists above our single triplet excitation that could be exciting two triplons at one time. And this may explain why there's a difference between the low field and high field part of this phase diagram. So when we go into that kind of mystery regime, you'll notice that that fuzz has kind of gone away. So that could indicate that something fundamentally in the system has changed. It could be that there's some change in the energy hierarchy. We really don't know. We can only kind of speculate at this point. But importantly, we still see this Goldstone mode here. And so this indicates whatever is happening with the system could still likely be approximated as a Bose-Einstein condensate. And so this is what really excited us, because now we have an idea that it might be a Bose-Einstein condensate, but there's something weird about it. And that's always what we scientists love, is when there's something weird that we can kind of probe at and investigate. And then just kind of for completeness, when we go to this high field regime, now it's essentially like you're measuring a ferromagnetic system. So you no longer have a Goldstone mode because all the spins are parallel to the field, but you do still maintain this spin wave excitation. And so with that, I'm going to kind of round out. So this was everything up to 2020. And so I'll kind of round up what we knew at the end of 2020. And this is published in our Physical Review Letters paper in 2019. So we found the first evidence for Bose-Einstein condensation in a rare earth-based magnet. So the rare earth being ytterbium. The ground state in the zero field, we understood pretty well. We were pretty confident it was a quantum dimer magnet, but we still had these unanswered questions about the magnetic field-induced states. And so to kind of answer that question, we decided to perform a second CNCS experiment. And at this time, I had actually moved to my postdoc at Purdue University, which I moved to in 2021, and working with my advisor there, Professor Arnab Banerjee. And we had developed this idea of, well, we wanted to understand what was going on in ytterbium silicate, but we also thought this system could be a phenomenal example for using a quantum computer to simulate a quantum system. But in order to accurately do that, we needed more neutron scattering data. So we proposed an experiment. It ended up getting an alternate or maybe status, as I like to call it. And eventually we were awarded the beam time. And so this is kind of where the story regarding the Laue comes in. So we were awarded this beam time June 16th of 2022. And so based off the timelines I gave you before, we're normally planning these experiments about 6 months out. They told me my experiment start date was August 1st. So at this point, we have about a month and a half, but it turns out you also have to have your sample at the instrument early. So we had almost only a month to prepare this neutron scattering experiment. And so Purdue is a very big, prestigious university, so they have a ton of scientific equipment. And in fact, they do have a Laue on their campus, but it was kind of across campus. And it turns out that the Laue that they had, which was not a Photonic Sciences Laue, just was not able to do the job that we needed it to do, co-aligning these crystals. And so we had ordered one for our lab at Purdue from Photonic Sciences, but we, I think, had only ordered it maybe a month before this time was awarded. So there was no way it was going to arrive in time, especially with still kind of COVID delays happening. And so what we decided was that my advisor would fly me back to the lab I did my PhD in at Colorado State. Luckily, many of the samples were already there, and I would use the Photonic Sciences Laue 1,000 miles away to align my samples. And so this is what I did. I flew out, and over the course of 3 about 12-hour days, I was able to take the sample from this original experiment and actually reorient it to another scattering plane so that we could apply the field in a different direction in the crystal. So you'll notice some of the copper pieces have fallen off. You know, obviously there were casualties in this. This was not an ideal way to do this. But this was something that was really really only possible by having a quality Laue available. And really, I had no concern spending the money to fly out to CSU to use their Laue, because throughout my PhD, I had used it and we never really had any issues with it. And so I ended up getting it shipped with about 3 days to spare. And we got absolutely gorgeous data that I'm showing here on the right. So I'm still working on the analysis of this. But this was with a different field direction. And you just see these kind of beautiful triplons or spin waves, particularly in the 5 Tesla data. And when we'll be using this to kind of back out more information about what is happening in the system. And so with that, I'll kind of summarize everything I've talked about and give you kind of the takeaways for what I've talked about. So we found evidence for an unexpected Bose-Einstein condensate state in ytterbium silicate, the first of its kind in a rare earth system. And my work is still continuing to fully understand the system. And this is actually a system that my lab here at Brock will be building off of. Additionally, I love neutron scattering. It is kind of one of the first things I started doing when I got into science as an undergraduate. And so I wanted to kind of show that off a little bit and show that it is this powerful probe to study condensed matter physics problems, or really most physics problems, aside from things like particle physics and astrophysics. And it's greatly complemented by X-ray techniques like Laue diffraction. In order to get these samples ready for neutron scattering, you can't put them in a neutron beam very easily. So having a Laue in your lab that you can take your sample immediately to and cut it or orient it or whatever you may need to do, I think is a really, really big advantage in a crystal growth or neutron scattering laboratory for that matter. And then, yes, I've already kind of said this, but yeah, these in-lab Laue diffractometers, like the one Photonic Science builds, allows for rapid iteration of crystal growth and preparation of single crystal experiments like the ones I showed you today. And so with that, I just want to thank all of the wonderful people who over the past 7 years have helped enable this work and take it to papers and things like that. As well as the National Science Foundation in the United States, who funded all the research that I've talked about here, and the Department of Energy, who runs the national lab I used. And with that, I'm happy to take any questions that you all may have.
I think there are a couple. So this is a 2-part question, I think, for you, Gavin. Number 1, is there an alternate method if you're not awarded neutron beam time? And with that, why was the on-site Laue not, what was it about the Laue that you couldn't support your work?
Yeah. So the first one, if you are rejected from beam time, obviously if it's a borderline case, you can maybe argue to a higher up at the lab that you should have been awarded beam time. If you are rejected though, it's generally, you have to apply next round or you need to go to a different facility. Really the main reason I think neutron proposals get rejected, 1 being just there not being enough time in general, and 2 being not having sufficient preliminary data to justify the experiment. Like I was saying, the national lab is spending, $300,000 or so on your experiment. And so they want to know whatever data you get is going to be good data and it's going to be publishable, because that's their metric. In terms of the Laue, yes, the other Laue, partly it was a reliability issue. There were numerous times I went to use it that, and this one required cooling water, that you would turn it on and it wouldn't work. Otherwise, we found their software to be incredibly lacking. You couldn't really actually solve your crystal structure very easily. And even if you did get a okay Laue pattern, it still looked nothing like the quality of Laue patterns I got from the Photonic Science's Laue. And so, yeah, I would say it's a reliability. And then I think in part it was, we weren't sure how much we could trust the answer. And also just their geometry wasn't very good for doing this. I'm not sure what their Laue was aimed towards doing, but trying to put in the sample mounts and things like that, and keeping their relative orientation was just not possible with the other Laue system.
Okay, so especially with the amount of costs that it takes to use a neutron, you wanted to have the confidence that your sample was ready to go so that you weren't wasting that neutron time.
Yes, yeah, exactly. Yeah, nothing is worse than if you get to a beamline and they start illuminating your samples with neutrons and you realize the whole orientation is wrong or something like that. So yeah, it was having something that we knew would work and would give us the right answer.
Very interesting. Okay, well, I learned a lot. I don't know about, let's see. Do we have any, so I get that. So you did mention that you would have to go to another facility, but is there another way, an alternate method, if you can't use Neutron, or do you just have to reapply?
So it really depends on what scientific question you want to ask. So I am often wanting to measure the excitations of the system in order to back out what the kind of, we call it the Hamiltonian or kind of the governing equation for the system is. In the case of magnetic systems, I think neutron scattering is the best way to do that. There are other methods that you can kind of get towards these answers. So you can actually get information on the Hamiltonian from heat capacity and all these other things. But neutrons are really kind of directly interrogating the energies of the system. And so that's what makes them so powerful. So X-ray scattering is starting to come up with some other techniques that kind of overlap more with neutrons. But I don't think neutrons are going anywhere for a while.
Okay. Then what is the main cause of narrow energy gap between Goldstein mode and spin wave excitation?
Yeah, so the Goldstone mode, go back to that here. So there's this gap here, which I think is what you're alluding to from the Goldstone mode to the spin wave. That one just comes from, so the energy of the spin wave excitation comes from how strongly the spins talk to one another. Whereas the Goldstone mode doesn't so much depend on how much they talk to one another. It's merely processing the spins around a field, which should cost zero energy to do. So the gap between them just happens to depend upon kind of two slightly different things. So this one has a relatively small gap. Other systems could have large gaps. Yeah.
Okay. I think, let me just check everything else. What is the maximum and minimum sample size that the system can index? I think, Rob, this might be for you.
Oh, yeah. I put in terms of the smallest, we using a microfocus X-ray source. I think the smallest one I've done is about 50 microns across, in terms of the smallest, and the largest standard system can probably accommodate a sample probably about 200 millimeters across, 250, but we could make a bigger system than that. We have made some very special large systems that can accommodate very large crystal balls that are quite tall, maybe 3/4 of a meter tall, something like that. And also turbine blades and things which are quite large and cumbersome. So yeah, we can make systems to accommodate a range of sample sizes.
And there's one more. You mentioned a cutting tool. After you have oriented the crystal, do you have to remove the sample to use the cutting tool, or how does that work?
Yeah, so the cutting tool is separate. Normally what you would do is orientate the crystal and then using the goniometer in the Laue system, and then you can either remove the goniometer and fit it onto your cutting tool with the sample on it, or we supply the goniometer with a transfer plate so that the crystal can be glued to the transfer plate, and then you remove it from the Laue, and then you set the same angles on the goniometer that you have on your wire saw. It doesn't have to be a motorized one, it could be a manual one, and you set those angles and then you cut it on the wire saw.
Okay. Gavin, I saw you shaking your head. Was there something different?
No, yeah, we used the first method that Rob was talking about, and yeah, I would add there that in comparison to this other Laue system I was talking about, the thing that I think one of the things that impressed me about the Photonic Sciences Laue is when we would do these crystal cuttings, we would cover them in this, I don't even know what the material is actually made of, but it's some sort of easily meltable plastic that will solidify. And actually you can measure the crystal's orientation even through a big hunk of this, this polymer that is holding it down to the plate. So yeah, the cutting, I think there's a little bit of an art to it. You got to get good at it, but yeah, the other system had no way to cut crystals. I don't think that was a mode of operation they expected. So yeah.
All right. Well, I want to thank both of you, Rob and Gavin, for your, this was very interesting. I know it was for me. I hope it was for everyone else. As I mentioned in the beginning, this has been recorded, so I will have this up on YouTube, and I will send everyone out a thank you. But again, thank you, Rob and Gavin, for your time today and your knowledge on Laue and all quantum mechanics, which is all new to me. So thank you guys very much, and thank you all for attending.
Yeah, thank you very much. Thanks for listening.
Yeah, thank you.
Cheers.
Yeah, thanks everyone. Bye.
Bye.
Bye. Bye.